So this is the core. It's where the most of the mass of the proton, for example, is concentrated. That will be 6 pion structures, each having 4 feathers, each feather having 35 MeV. And this is the fur coat. As you can see, it's much larger because its own energy is much smaller, like 6 times smaller than this guy. So it's roughly 6 times bigger, right?
Greetings, this is Eugene the Philosopher, the greatest living philosopher after the unfortunate passing of Quentin Robert D. Nameland, who has been the greatest living philosopher before me. So in this video, we are considering what I promised you, like 2 videos ago, when we were discussing Kyriakos' theory of elementary particles. So I promised you to make another video about another phenomenological model of Burtaev, of elementary particles as well. And this is the video about that. So let's begin.
Alright, so we shall talk about the theory of this guy, Burtaev Yuri Vasilievich. As you can see, he's no longer alive, sadly. Like, who is he? He had an engineering background. He even wrote like some engineering textbook on something electrical, roughly speaking. He also served in the military. He actually was a colonel, I think. So mostly dealing with stuff like anti-air defense and like radio-electronic warfare and rockets and things like that. But we are here for his studies of elementary particles specifically. So I'm gonna link all of this this website if you're interested. So he has written quite a bit of books about this. Unfortunately, all of these books are in Russian, but you can still download them and maybe use a translator or something because the text is searchable. Okay, and like you can put it in Google Translate or whatever you prefer. So as you can see, there's quite a lot. So he has published them since 1990s. Okay, so first book. We're gonna mostly be focusing on this, the very first one from 1995. But then there are some books about nuclear physics that's we're definitely not gonna talk about today because it's a whole separate topic. And then a couple of more. So as you can see, quite a bit of books. So from reading those books, what I can say right away is that there's quite a lot of work that went into their making. So a lot of research, like literally a few decades of research, is summarized in these books. So a lot of work has been done, and it should be respected, in my opinion. All right, so we shall look into the first book. What does it tell us? I actually want to open my notes here. So unfortunately, yeah, the books are in Russian. One funny part about this is that in this book, at the very least, the very first one and a couple of next ones, perhaps he continues it into the others as well. There are exercises that he proposes. Like after each chapter, there's like a small section with exercises where he says like, do this, calculate this, like think about this, like what can we conclude from this, etc., etc. And it's kind of funny actually. Like this is an attitude I have never encountered previously in any alternative science circles, and it's very refreshing actually. All right, so we previously talked about, I'm gonna link the video in the description, about Kyriakos' model of elementary particles as like Kelvin-esque knots, okay? So I would claim, in order to explain to you better what Burtaev is doing, that Kyriakos was focusing on ontology. That is what the stuff is, right? So he was trying to build a model of elementary particles based on what they are. Whereas Burtaev's approach is actually quite a bit different. He literally calls this, his books, like somewhere here you can actually see, it's a draft of phenomenological description. That's literally what he calls his research, okay? So what is phenomenology? Like, as opposed to ontology, which is considering what the stuff is, phenomenology considers more like how the stuff looks and behaves, or even better so, the relation between stuff, the relations between objects, and not their fundamental nature. So Kyriakos was considering the fundamental nature of stuff, and Burtaev is mostly considering the relations between objects. So we are going to be dealing with a very low resolution view, which is somewhat unpleasant, but by necessity it is what it is. At the same time, this fact that we're having a very low resolution view allows it to be much broader and to be more practical. So as I've said, decades of research summarized briefly. At least I'm gonna well, make some sort of an introduction, okay, of you towards Burtaev's theory. Right, so at first, like, he begins with some quasi-philosophical considerations in this book. He talks about what he calls substance, which basically, again, the substance organizes itself in such and such kind of way, and we get like elementary particles as one of the consequences of such self-organization, if you wish. You may call this substance, this is my commentary, okay, this is not Burtaev anymore. We may call it ether, if you wish. You may call it electromagnetic field. You may call it something else, like you may call it John, okay? We just don't really care. Burtaev calls it just substance. And he says that substance forms these structures, okay? This is what we're going to be dealing with. And so it's all kind of vague, okay? So you just kind of, I don't know. We just have to run with what we have. So some vague substance creating structures, all right? What kind of structures, like what it is exactly, it's not really clear. So again, low resolution, phenomenology, okay? So we're going to be dealing with some fundamental categories and values, and here I'll show you from the book. So we have space, we have time, we have motion, and the only quantities we're going to be dealing with constantly are the speed of light c, Planck's constant h, and fine structure constant alpha, and also pi, of course. And everything else we derive, okay? So these are the only numbers which are like considered to be given, all right? And everything else we shall derive. So yeah, this is, we've already talked about. You can derive from these quantities the electric charge, for example. I mean, it's pretty well known. Or vice versa, you may derive alpha from the electric charge if you allow the electric charge to be given, all right? So yeah, alpha and electric charge are elementary charge. I mean, they are kind of mutually replaceable. So let's talk about the electron, which is the most important particle probably for any alternative theory, okay? So Burtaev says that electron is some sort of a finite or localized excitation of space. Finite meaning having a finite size, all right? So it's localized in space. Or you may call it not space. I think this is a quote because I took it in quotation marks. But maybe also you can call it excitation of substance, all right? Not just space. But whatever, that's all terminology. What is important to us is that in the near field, so that is when you are very close to it, it represents this sort of rotating three-dimensional oscillator with a dynamically stable structure. So right here, right away, this is what I was warning you about. Like the problems begin in the sense that we don't really know what is oscillating. And we don't even know precisely how it does so, okay? So it's something rather vague. Like what is rotating, what is oscillating? That's not quite the electric field. That's not quite the magnetic field. That's substance, you know, something in the substance is doing this. However, there are some properties which are clear. Like for example, Burtaev requires electron to have an axial symmetry. So there's a symmetry around the z-axis, roughly speaking. And again, a dynamically stable structure. What does dynamically stable means? It means it's kind of self-renewing, so it doesn't disappear, you know, it doesn't dissipate. It's kind of renewing itself on each next oscillation. So it basically can exist for eternity. That's what dynamically stable means in this context, at the very least. So, and he also says that you can, roughly speaking, subdivide this vague oscillation into a transverse, which he calls turbo. For some reason, that's a term he invented. And longitudinal, which he calls auger excitations, okay? So in electron, apparently, according to Burtaev, there are these two different oscillations. One is transverse, one is longitudinal. And they kind of induce each other with this phase shift of pi over 2, or 90 degrees if you wish. And plus, everything spins around z-axis. So I'm going to show you some pictures. And once again, I will reinforce my point that I have no clue what is depicted here, okay? Just so you know, like if you are confused, so am I. It's just something is oscillating in this plane, something is oscillating in this plane. So these would be like the what he calls auger and turbo, right? Transverse and longitudinal, and all of this is rotating around z-axis. How exactly? Like what is it exactly? Like what is it oscillating? It's not the E vector. It's not the B or H, you know, the magnetic vectors. It's something, okay, but we don't really know what it is. And by the way, one single thing like this is another term which we'll encounter later. He frequently calls a feather, like he literally calls it that this is a cross section of the feathers of auger in the plane ZY, and the crests of turbo in the ZX axis. So these guys, like one is, like roughly speaking, vertical, this guy, and this guy is also actually vertical, but it's kind of transverse. It's very confusing, all right, at least to me. But generally, at least on some semi-intuitive level, perhaps you can get the idea that it is some blob of substance which is kind of like oscillating like this, okay? Now it's all rotating around Z. Like again, these pictures don't really help a whole lot to me, at least. So, like, I don't know, maybe you can make something out of them, but I cannot, sadly. I've tried, all right? And there's nonlinear stuff around this structure. So this structure is like it's like a zeroth approximation, or what they call in QED, quantum electrodynamics, what they call bare electron, right? Electron on its own, isolated from everything. But the electron is clearly not on its own. It's never isolated from anything. So there is a substance around it as well. And it is kind of hooked to it, at least slightly, right? It interacts with its immediate environment. And some other effects follow from that, but we'll come to this later. So, yeah. So electron is also allowed to have only one and not more specific value which can be experimentally measured. I mean, there has to be something special around about the electron. You can't really derive it fully from just CH and alpha, right? And Burtaev says, well, let's just consider this extra degree of freedom, its energy, 511 keV, right? And then we can derive everything else, like angular momentum, moment of inertia, like some like provisional units of acceleration, maybe temperature if you wish, elementary current, some proper current, proper voltage. I'll show it to you in a moment. Magnetic moment, magnetic flux. Okay, and we'll talk about this slightly later. So that's 35 up to 39. Let's go and look at it. Oh shit, sorry. Okay, so this is our measured mass, essentially, or energy if you wish. So we can derive frequency by just dividing the energy by h. We can divide the period, can define the frequency, the angular, frequency, right? We can find the wavelength, blah, 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 blah. We can find basically spin, that is angular momentum, right? We can find, well, all these other quantities, basically, right? You can even ascribe to it certain temperature, if you wish, if you divide the energy by Boltzmann's constant. Elementary current, etc., etc., etc. So everything is easily derivable. That's the idea. And then, as we've just mentioned, there's a substance also around the structure, right? Not only substance forms the structure itself, but also exists around it, and this is what he calls valento. It's again the term he invented to the nearest excitation of otherwise free space, right? So the presence of electron excites this space or substance, if you wish, and the characteristic energy would be the energy of the electron itself multiplied by alpha squared. So you can basically, like this nonlinear interaction, you can reduce it to series in the powers of alpha over pi, okay? And so that the next order, next to leading order, so to speak, would be alpha squared, and that corresponds to the energy of 27 eV or about so. And then the size of this thing, if you calculate it, it's equal to Bohr radius, okay? Yeah. So some other points that he considers is that the electron has opposite rotations around z-axis of this Auger and turbo, sub-oscillations, I guess, of electron, transverse and longitudinal. And in the positron, they coincide. So that's how you get the opposite electric charge. By the way, in Burtaev's approach, there is no such thing as like charge density, if you wish. So charge is not distributed within the structure, but charge is an integral characteristic. Basically, you can only talk about electric charge from far away. When you're looking at, for example, electron from far away, and it kind of, you can no longer distinguish these parts, you know. When it looks like a dot for you, then it has electric charge. But the charge itself, if I remember correctly from some of the interviews I've watched with him, he said that it relates to the mutual orientation of these rotations of inner parts of the particle, okay? So that's what charge is, essentially. Yeah. But it's an integral characteristic. It's not spread out in it. There is no such thing as charge density. It's pointless to talk about this, okay? Well, hopefully, I know it's rather vague, but I warned you, okay? Okay, then he talks about annihilation of electrons and positrons, right? Where we have orthopositronium, parapositronium. He actually considers, what's the page? Didn't put it here. Well, somewhere like 54 maybe. He considers different arrangements. So this is the, by the way, this is the one of the exercise sections. So you can see, like he says, well, calculate this, take a look at this, approximate this, blah, blah, blah. So, well, here he, I think, demonstrates different rotations for electron and positron. Again, it's kind of very vague, right? Like, unless you really know what is happening here, like, you won't be able to understand it clearly, right? And like I tried, I've read it, and I still cannot imagine what is happening here. But I'm kind of fine with just stating, okay, there is some oscillation. One is longitudinal, another is transverse. Okay, what is oscillating? We don't really know. But at least we can, like, crudely calculate some stuff. We can make some ratios at the very least, all right, of all of this stuff. And this is good enough, maybe. So this is a parapositronium, and this is... wait, this is ortho, okay? And he actually like does some hand-waving type of explanation why one lives much longer than the other, according to his model of these oscillations, let's say clockwise and counterclockwise, etc., etc., etc. Yeah, another exercise section, like calculate this, calculate that, think about this, think about that. And all right, so this is his idea of electron, essentially, right? And let's talk about pions. What are pions? That is Pi-mesons. So if we have electron-positron annihilation at around 300 MeV, almost 100% of the products of such annihilation turns into Pi-mesons, okay? So the idea of Burtaev about Pi-mesons is that they are just double electrons. That means if in an electron we've had two of these feathers, so basically one half here, one half here, right? So one feather here, one feather here. For both this auger and turbo, both of them have two feathers. Then the Pi-meson, in his view, is actually four feathers. So two feathers would be electron, four feathers is a pion. But because it has a much bigger mass because of this, because like the energy is much bigger, because you have four feathers instead of two, it will also be much smaller, okay? So it will be alpha times smaller than the electron, basically. And like further, like once we transition from electron to pion, Pi-meson, we transition to what he calls a hadronic sector. I mean, it's kind of considered right now that Pi-mesons are hadrons, okay? And all hadrons, according to Burtaev, are combinations of these harmonics with the energy of E will be the electron energy divided by 2 times alpha, okay? So this is basically one feather. This is the energy of one feather. So you divide electron by 2, you get 1 feather instead of 2, and you also divide it by alpha to get into hadronic sector from the electron sector. I hope it makes some sense for you, okay? But again, when we increase energy, the spatial scale decreases. And Burtaev claims that it decreases alpha times, because again, we've already agreed that we're only going to work with H, C, and alpha, period, right? And we only measure the electron's energy, 511 keV. So 1 feather will thus be able, and we can calculate it like this, okay? But it's only when it's in hadronic sector, right? For electron itself, this feather wouldn't have this energy, obviously, all right? It would be just half of the electron's energy without alpha. But when we're getting to pions, it's times alpha. And when we're dividing by alpha, actually, we're multiplying by 137, right? So that's why a pion is much heavier than electron. So we have electron energy 0.511, and thus 1 feather, if you calculate it like this, will have, well, this is quotation marks, so this is how Burtaev talks about it, 30 to 35 MeV. Why is it not exact? It's actually 35 if you calculate it, but he like various, again, of those nonlinear sort of interactions with the immediate, the substance in the immediate vicinity, like this valento that we've seen above, they may decrease or increase this value, right? So that's why we have this corridor roughly. But roughly, he says, 1 feather is roughly like 35 MeV. And you build all the hadrons from these feathers. Long story short, okay? So all the spatial characteristics of a pion are 2 divided by alpha, smaller than the electrons. So here we calculate the wavelength, the period, something. And also, like, if in case for electron, we could never have zero charge, it's either electron or positron because there's only 2 feathers. Here with 4 feathers, a pi zero particle is possible, okay? The one which has no charge. And again, the charge here represents kind of the mutual arrangement of these rotations of various of these feathers, okay? So just like in positron, maybe I've actually written it here. So in pi plus, the auger and turbo, so that would be the transverse, I think turbo is transverse. The longitudinal and transverse oscillations, sub-oscillations if you wish, rotate in the same direction around the z-axis, and it's kind of the analog of the positron, so that's how you get a plus sign of the charge, right? And in pi minus, they rotate in the opposite direction, kind of like in an electron, except in electron you only have 2 feathers of both auger and turbo, and for pion you have 4, right? So there's a quite confusing thing about him talking about slower rotation. Basically the idea is, how do we still get h for spin? I mean h over 2 or whatever. So I think this is my kind of deductive reasoning from what he wanted to achieve, and I think that was his point, even though he formulated it quite differently. Like, he literally says that pion rotates slower, which doesn't make any sense for me, because to have the same angular momentum, right, if your structure is spatially much smaller, it has to spin much faster, right, to get the same angular momentum. So I would say that maybe he misspoke or something. So because it should be faster rotation, I think, because with smaller size, to get the same angular momentum, you need faster rotation, not slower, right? So yeah. So yes, pion is smaller, but then again, it's my understanding. Maybe I completely misunderstand it, but I think what he says is that since pion is smaller, it has to rotate faster. And how faster? Like 2 over alpha, right? Times, yeah. And in pi 0, we have the opposite feathers rotating in the opposite direction. So they represent sort of like standing waves. Again, it's all very vaguely, okay? Like it's very hard to imagine, like what are we even talking about here? So thus pi 0 is its own antiparticle, and it has no valento. He actually sometimes calls it gluono when we're talking about hadrons specifically, but it's the same thing. It's like the nearest area to our particle, right? Which is kind of interacting with this particle through, well, whatever way the substance interacts with itself, okay? We're not even talking about electric fields again. We're talking about something vague, some interaction. And thus, we say there is no electric charge, right? So why no valento is because it's kind of locked onto itself, right? Like it's standing waves. They don't, you know, how do you say it? Creep into the nearby space. They're completely locked. All right. That's why I don't have an electric charge, which once again represents kind of a long range interaction of substance. Right. When you look at the particle from far away, then it has this integral characteristic as electric charge, for example. So pi 0 doesn't have it. And it has lower mass because, again, it's not hooked onto the near space, right? Doesn't drag extra excitations. This is my comment. Okay, so if we look at the decay of Pi-mesons, what do we get? We get muons and neutrinos. So let's talk about these guys. Probably something important on this page. Let's take a look. Well, no, it's just pi decays into anti-muon and neutrino, or muon and neutrino, all right? So how does it happen? Well, according to Burtaev, one of the feathers, I'll remind you that pions have 4 feathers, so one of these feathers, each one having this energy basically, breaks off and turns into a neutrino, and since the feather had this roughly 35 MeV energy, it has to be distributed between the resulting muon and a neutrino. So basically from here you already get that the muon is just the 3 remaining feathers, right? With total energy of roughly 35 times 3, 105, which is almost exactly the mass of muon, by the way, just so you know. Yeah, and the remaining energy is divided between kinetic energy of this guy, the muon himself, the 3 remaining feathers, and some of it is taken by neutrino. Now, in Burtaev's theory, neutrinos are massless, so they just represent, so neutrino moves with velocity c because it's massless, and it represents something like a longitudinal excitation of space. That's how Burtaev himself describes it, okay? And since the feather had angular momentum along the linear velocity, we get chirality for a neutrino, all right? So, yeah. Well, there you go. Thus, muons are just 3 feathers combined. So they are separated by 120 degrees, right? Something like that. Like a 3-phase generator or something like that, 3-phase electric motor, right? To 120 phase shift. Since it's an odd number of feathers, there are no standing waves possible. So mu0, roughly speaking, is impossible. Then it has the same spin, so it's also smaller, but it rotates faster than an electron. Then, well, as we've discussed, breaking off of one feather is the primary mode of decay. So 2 remaining feathers, we're talking about muons, sorry, I confused myself actually. So muons decay with breaking off of one feather again. So 2 remaining feathers will form an electron, but they have to like expand in size, right? Because we saw that the pion is alpha times smaller than the electron, and therefore muon is also roughly the same size as a pion. But in order for these feathers to turn into electron, they have to expand alpha times, not alpha, like 1 over alpha, like 137, right, times bigger, basically, right, to form an electron. And also we get the neutrino, and also we get the energy. So this feather has 35 MeV. Then we have an electron, which is only 0.5 MeV, and a bunch of energy pumped into the electron itself and a neutrino, right? So this is a kind of a big problem, which Burtaev devotes like a few paragraphs to. Like how exactly is this electron, which is very light, forms from this, really heavy particle, such as muon. Again, electron is 0.5, and muon is 105, right? So that's 200 times more, 200 plus times more. So he actually says that like it's very complicated. It's actually not a couple of paragraphs. It's like 4 pages or even 5 pages. Like I've read it and I cannot tell, okay? Like there is no simple answer. Like he just considers different angles, like how is it gonna fly apart. You can see there's some cosines, and like apparently like this hand waving sort of explanation, it has some experimental not even proofs, I don't even know how to call it, like some experimental hints that it is correct, but there is no explanation from a capital E, something like that. Yeah, so it's complicated. Then the energy difference between muons, like 3 feathers, and the muon exact mass could be caused by this gluono, or the interaction with the nearest area of space, and it's of the order of 1 MeV. All right, now let's talk. This is probably the last we're going to talk about, because this video is already quite long. Let's talk about his picture of nucleons, that's protons and neutrons. So he just postulates that a proton and a neutron are just 7 pions combined. So that would be 7 times 4. I'll remind you that a Pi-meson has 4 feathers, according to Burtaev, each having roughly 35 MeV energy. So 7 of these pions would be 28 feathers. And here's my question to myself and you and Burtaev and everyone else, like why is that exactly 7? Why not like 2? Why not 3? Why not 4? Why not 5? Why not 6? Why is it 7? And I don't know. that's my answer to my own question. But well, somehow it makes sense if there's 7, okay? At least empirically, like we can measure the mass and we can say, okay, this looks like 7 pions, okay? So the energy is 28 times, well, here you can see we're already not using 35 MeV as a metric, but 33.5, and then we arrive at 938, which is the mass of the proton, right, roughly. So since we have the odd number of pions, I actually have no idea what I meant by this. Oh yeah, so again, the odd number means that, we don't have these, roughly speaking, standing waves again. So sometimes this structure will have only longitudinal polarization, which again Burtaev calls auger, or sometimes only transverse, and it kind of oscillates back and forth. Again, it's all very vague, right? It's a low resolution view. And also, due to the odd number, this is kind of a more philosophical / aesthetic claim. The stability of the structure can only be achieved with hierarchical structuring, with integer ratio between parts. So it's not just a lump of 28 feathers, but they have to organize into some sort of a Russian doll type of structure, something to that effect, right? Hierarchical structure. Not just any hierarchical structure, but with integer ratio between 2 parts. Or at least 2, right? And he says that the 6 and 1 is the only possibility. So 6 pions would represent one substructure and 1 pion would be another, all right? Because again, you can't, like if you take the number 7, you can't divide it into 2 numbers, into sum of 2 numbers, which would be integers ratio of each other, right? Except for 6 plus 1. It's not 2 plus 5. You can't divide 5 by 2, right? You don't get an integer. It can be 3 and 4, and the only other possibility is 6 and 1, right? And that's how it works. So he calls these parts Kern. That's a German word. It means core, so we can just call it core. He usually uses K to depict like provisionally name it, basically, okay? And so what is the core? It's this inner part with 6 pions, or 24 of these feathers. And there's also a fur coat, or like the outer part, with only 1 pions, with 4 feathers. So let me show you the picture, so you would understand what we're talking about. So this is the core. It's where the most of the mass of the proton, for example, is concentrated. That would be 6 pion structures, each having 4 feathers, each feather having 35 MeV. And this is the fur coat. As you can see, it's much larger because its own energy is much smaller, like 6 times smaller than this guy. So it's roughly 6 times bigger, right? In terms of size. And this is... Okay, so some more considerations. He says mostly they annihilate. I mean, if you take proton, antiproton, they would annihilate into pions. And he says, well, clearly that hints that they're made of pions, right? In a neutron, the core and the fur coat have opposite turbo rotations, and thus they have 0 charge. In a proton, the core is actually at 2 standing waves. So it's kind of like a Pi-meson, but 6 times more of them, right? Because there's six pions. Hence, no turbo rotation, and the fur coat has rotation, and it actually determines the proton's charge. And he bases these statements on the experiments of Hofstadter, who received the Nobel Prize for them in 1961. So we know, for example, how the charge, in air quotes, is distributed in a proton and a neutron. And it definitely looks like there are 2 different structures within them. So this is the proton, for example. He claims that this is the core, and this is the fur coat, all right? And this is like the gluono, right? The nearest the space around the proton, which is slightly excited by the presence of the proton. It's kind of hooked onto it, right? And for neutron, we get this. This is the core, and this is the fur coat. So as you can see, it's roughly 6 times bigger than the core. Just how like our simple phenomenology requires. Because there's only 4 feathers here, and there's 24 here. So this must be 6 times bigger than this, spatially. Because, again, mass or energy is inversely proportional to the size. You can probably invoke some sort of philosophical argument that if the substance has a constant density or something, then the heavier things would be smaller, or something to that effect. I don't know. It just came to my mind, but it doesn't really matter. If it doesn't make sense, just forget it. And then we calculate a whole bunch of stuff for this, for these structures, for nucleons, essentially. From following what we've just talked about, like magnetic moments, and things like that. So, and again, once again, we have the exercises, all right? Yeah, so later on, he talks about the resonances like tau, sigma, rho, eta, omega, whatever particles, right? And he has tables. So most of these particles are also made from these feathers. Actually, all of them are made of these feathers. This is the number of pions in the core. Q is for the core, and actually, wait, I might be misinterpreting, because I thought the K is the core, and he actually has Q for the core. Oh, no, it's correct, actually. The core is here, okay? This is the core, and this is the fur coat. So this is in pionic units. So 1 is 4 feathers. Each one is a 4 feathers, right? So 3/4 or 3/2, that would be 1.5 times 4, that would be 6 feathers, right? 3/2 is 6 feathers. In the fur coat, for example, of rho particles, right? Etc., etc. And this is the ratio between core and the fur coat. It's also always integer, as you can see. So these are these particles, these resonances. Then there are these particles. Also, this is the core fur coat in pionic units. So each 1/4 is a 1 feather. So these will be 3 feathers here, 12 here, blah, 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 blah. And as you can see, there's quite a lot of stuff, quite a lot of work that has been done. And you can calculate, at least Burtaev does for some particles, he calculates again like magnetic moments, he calculates all kinds of stuff. But wait, I'll just show you how much of the stuff there is. Once again, you can download the book. Of course, it's in Russian, but you can still look into the tables and like get an idea of how much work there has been done here. And yeah, one thing which I'm pretty sure you aren't aware of, which I wasn't aware of, is check this out. The quark model actually ignores some of the resonances. So Burtaev, like I've shown you, at least some resonances, how easily they can be described with this scheme, with these roughly speaking feathers, and this hierarchical division of structure into the core and the coat. So the quark model actually ignores some of the resonances. So the experiments show clearly that there is a resonance at some energy. And the quark model says, well, excuse me, but I cannot describe this particle with a quark model. Therefore, there's no such particle. All right? So they literally call them false resonances. I've never heard about this, by the way. Like, it's only through Burtaev I've learned about this, because it's all swept under the rug, right? Just because we cannot see it, because quark model cannot describe it, you forget about it. It's not a real particle. It's a false particle. But the resonance is there. I mean, you can look at the experiment, but it's one of those cases when, you know, what they say, like, if my theory is contradicted by your experiment, well, sorry for your experiment, you know, it's your problem. It's not my problem. The theory is correct. The experiment is wrong, you know. Basically, so as an example, there is this particle tau 725. 725 is a mass in MeV. There's so-called A1 particle. There's a so-called ABC effect. These are last names of Abashi and Booth and Crow, etc., etc. So it's kind of big, isn't it? You can clearly see like how much ignorance was required for the quark model to succeed. Kind of crazy, But yeah. There goes that. This is Burtaev's Phenomenology, just as he himself calls it. It's a draft of a phenomenological description, where we're dealing with some oscillations of substance, of, unfortunately, again, quite unclear nature, and even like the exact dynamics is very, very vague, at least to me.
Alright, so to conclude, Burtaev presents this sort of rough, low resolution, what he calls a phenomenology of elementary particles, and I think it's quite captivating. Though it has certain downsides, which I probably already mentioned, but let's kind of sum them up. So in my opinion, there's quite a bit of hand waving, which is not good. So a lot of the stuff we can't even imagine how it looks. I mean, understandably so, because he himself calls it just a phenomenology. It's not even a model if you think about it. It's something approximating a model, in the words of Jordan Peterson, okay? So yeah, like for example, when I was preparing this video, I was thinking about maybe making a like 3D animation or something of you know, these structures, like an electron, for example. But like I very quickly realized that I can't, because I have no idea what I should animate. Like what exactly is oscillating? Like how exactly it's oscillating? How is it rotating? Like I have no clue, to be honest. And again, you probably saw how, well, very vague it all is, okay? So we just have to kind of concede. We just have to admit, you know, kind of relax and have pleasure about it. Like that we can't really depict it properly. Maybe you can actually. Like again, maybe your three-dimensional vision is much better than I have, but I still have no clue what we're talking about. But I am kind of more or less fine with just talking about some roughly speaking, abstract harmonics of something, you know. I'm kind of good with this, and in this sense, I really like this model, okay? So, another downside of it is actually having, introducing new terminology, which I would claim is always bad for any new theory. By the way, if you want to have my coaching for your own theory, watch till the end of this video. I'll advertise my own services in this respect. But still, introducing any new terms is always a bit of a suspicious moment, okay? Like, why wouldn't Burtaev just call it something like longitudinal and transverse harmonics, for example? Why did he have to introduce this term of like auger and like turbo? Like, they're just so kind of stupid, actually, right? They're so weird. Then there is no explanation, or at least I haven't found one, of this transition between the electrons and muons, right? There's like several orders of magnitude of difference in mass, for example, right? So there's like a barren wasteland between them. So, but I mean, to be fair, no other theory, at least to my knowledge, has an explanation for such a transition. So it's kind of fine in this respect. But what I'm saying is, this theory doesn't look complete, okay? Burtaev's theory doesn't look complete. At least to me, at least initially. That was my initial reaction. Maybe if you think about it, maybe if you consider everything, then it would be better. Again, no real explanation in my eyes why protons should have like 7, protons and neutrons for that matter, exactly 7 pions in them, right? Why is it 7? Like, again, it's kind of weird. I mean, at some point, again, he says about phenomenology, so he just describes what already is, you know, what is known. So we know there are structures like protons and neutrons, and they kind of look like they're 7 pions, okay? Then why not describe them as such? Okay, upsides, good things, okay? So I really liked this sort of heuristic that the author uses with exercises in every chapter. It's kind of funny. It's kind of good, actually. Like, it introduces this mood of like, we're just asking questions here, you know. Let's play with it a little bit. Let's try to, you know, poke the problem here and there. Like, let's be curious a little bit. So that's certainly not anything that you see in any of the alternative theories, actually, right? Like, their authors are usually like overly pompous and whatever, but this guy just says, well, try this, and see if you come up with something interesting, okay? That was really, really funny, in a good sense of the word, okay? Then, I believe, just like Kyriakos's model, again, I'm gonna link it in the description, that we've considered previously, it shows that it's very insightful to look into the intrinsic degrees of freedom of whatever particles we are considering, right? Because they clearly have inner structure. Again, the very fact that all of these particles have spin, i.e. internal, well, okay, not all of them, but most of them, okay, have spin, that is the intrinsic angular momentum. It means something is moving inside of them, which means they cannot be dots, you know, mathematical points. It's just pointless, pun intended, to speak about angular momentum of a point, alright? Because what is angular momentum? It means something is moving, but in a point, there's no space, there's no room for anything to move in, right? So it cannot be a point-like object, period. If you think it can, like, there's probably something wrong with you, okay? Like, again, in the middle school, in my country, in 7th grade, people learn what movement is, okay? Learn the definition of movement and try to, like, if you don't see a contradiction here, then I'm sorry. I'm really sorry. Okay, then one other upside is that these structural assumptions that Burtaev makes actually compare well to experimental values, at least everywhere where he considered them to be. Maybe there are some anomalies which we haven't considered, at least in this video, but I mean, we'll see. For example, the fact that Muon is having almost exactly, I mean, very close to 3/4 of pion mass. Like, currently, in the current quantum field theory, Muon has no relation to pion whatsoever. Then how would you explain this interesting coincidence? I mean, the current quantum field theory cannot. It just cannot, period. But the Burtaev's model, it shows where it comes from, and it comes very naturally from his model, right? Again, I'm not sure how far in this video I've actually came, the video you've just watched, because again, I'm recording this before I'm recording everything else, paradoxically, well, for some logistical reasons, quite obviously. So I don't know how far we've come, okay? So my plan was to consider at least one book, but there's many of them, right? So I don't know if I've considered what I wanted to talk about further, but let it be a spoiler for the next videos, because I want to continue. Like there's still quite a lot of stuff to talk about if we haven't talked about this already in the previous parts, which I think we wouldn't. Okay. So then the next thing I want to look into is the statistics of particles. Perhaps this we've already talked about, and specifically nuclear physics. So Burtaev has also developed, I mean, on the same kind of rails, the approach to nuclear, let's say, reactions, etc., like nuclear structures, which I think would interest a lot of people as well. So I'll definitely make a probably separate video about it, actually, okay? Soon-ish, 2 weeks from now, roughly. Maybe a bit more, because I still need to learn myself, all right? Yeah, so there you go. Overall, I think, at the very least, again, since all these books are in Russian, like I'm almost 100% sure that almost none of my viewers and general, let's say, English-speaking population is even aware of this model of Burtaev. So therefore, I mean, and the model itself is good enough, if you ask me, okay? So it's a good starting point. So that was my motivation for making this video. Well, thank you for watching. The eons are closing. If you wish to support me, please consider joining my Patreon. That is patreon.com/philosopher. See the link in the description. Or if you have a scientific theory of your own and you'd like my help in developing it, please join my alternative science coaching program, also available through Patreon.